Hey everyone, in this video we're going to talk a little bit about how to take the derivative of our inverse trig functions. The first one we're going to look at right here is y is equal to the inverse sine of x, and before we take this derivative we want to make sure that we make note that the inverse of the sine of x is not the same thing as 1 over the sine of x, right? Those are not equal at all, right? The one on the left is the inverse sine, and on the right that would actually be the same thing as the cosecant. So the inverse sine and the cosecant are not the same thing at all. So we don't want to think of those as being equal. So instead, in order to take this derivative over here, we're going to have to say that the sine of y is equal to x. We're just going to take the sine of both sides, and now we can use some of our implicit differentiation to say that d dx of the sine of y is equal to d dx of x. So on the left side here then, derivative of the sine of y with respect to x is going to be the cosine of y dy dx. And on the right side, this is going to come out to equal 1. And so in order to get dy dx by itself, we're going to divide by the cosine of y. So this is going to be dy dx is equal to 1 over cosine of y. Now I know that division there is going to be allowed, or in other words, it's going to work because that the cosine of y is actually never going to be undefined in this case. And the reason I know that's true is because the value of y always has to be between negative pi over 2 and pi over 2. Remember that y is equal to the inverse sine of x, and I know that the inverse sine of x is always going to give a value in either the first quadrant or the fourth quadrant. So the inverse sine of x is always going to be somewhere in that first or fourth quadrant there, meaning that y in this case is always going to be greater than a negative pi over 2, but less than a positive pi over 2. So what this tells us then is that the cosine of y is always going to be the cosine of some value between negative pi over 2 and pi over 2, and the cosine in the first quadrant and the fourth quadrant is always going to be a positive. And since it never equals pi over 2 and it never equals negative pi over 2, the cosine is never equal to 0. In fact, the cosine is always less than or equal to 1, but greater than 0 in this case. So not only do I know that the cosine of y is never going to equal 0, I actually know it's always going to be a positive value. So when I look at my identity, my Pythagorean identity, the sine squared of theta plus the cosine squared of theta, I know that that's equal to 1. And if I manipulate this, I can say that the cosine of theta is equal to the square root of 1 minus the sine squared of theta. And normally I'd have to worry about a plus minus in front of the radical, but again, because I know that the cosine is always going to be positive, I know I'm only going to use the positive square root in this case. So how does that help me? Well, instead of having cosine of theta, what I really have here is cosine of y. So I can just say now that dy dx is equal to 1 over the square root of 1 minus the sine squared of y. And again, I remember from up here that our sine of y is equal to x, so really all this is dy dx is equal to 1 over 1 minus x squared. So really what we figured out here is how to take the derivative of an inverse sine. From now on we can say that d dx of the sine of some differentiable function u, the inverse sine, is going to equal 1 over 1 minus u squared du dx. We just have to make sure we account for the chain rule there. And so we can take the derivative of any one of our inverse trig functions through this manner. We can say that y is equal to the inverse trig function of x. Take that trig function to both sides, so you have the trig function y equals x. Use implicit differentiation, and then use whatever identity is necessary. So real quick, we don't have to go through all of the algebra for them, but I'm going to show you what each of these derivatives actually is. So for sine, we just said it. We're going to say that the derivative of the inverse sine of u is equal to 1 over the square root of 1 minus u squared du dx. Okay, just make sure you account for that chain rule there. Well, the cosine, or the inverse cosine, cosine of u is simply just going to be the opposite of the sine. I know that the derivative of a cosine is just a negative sign, so same thing here. If I take the derivative of an inverse cosine, I'm just going to get a negative 1 over the square root of 1 minus u squared du dx. And if I do the tangent, d dx of the tangent, or inverse tangent of u, that's simply going to equal 1 over 1 plus u squared du dx. And just like sine and cosine have that special relationship where one is positive, the other is negative, tangent and cotangent have the same thing. So we have d dx of the inverse cotangent of u, that's going to equal a negative 1 over 1 plus u squared du dx. The next one, we have the derivative with respect to x of the secant, or the inverse secant, of u, and that's going to equal 1 over the absolute value of u times the square root of u squared minus 1 du dx. And sine and cosine are opposites, tangent and cotangent are opposite. You can probably guess that secant and cosecant are just going to be opposites. So I could say that the d dx of the inverse cosecant of u is going to equal a negative 1 over the absolute value of u times the square root of u squared minus 1 du dx. Okay, and if you look these up in any textbook, it's going to have some qualifications with a couple of them. For example, with the sine and the cosine here, it's probably going to have a qualifier that says that the absolute value of u has to be less than 1. And the reason for that is because if I take a value of u that's greater than 1, or has an absolute value greater than 1, then when I square it, I'm going to get a number bigger than 1. So it's going to be the square root of 1 minus something bigger than 1. So I'm going to get 1 over square root of a negative number, so that's going to be imaginary, and then the derivative wouldn't exist. Well, the same kind of thing is true down here with the secant and the cosecant, where we would say that the absolute value of u has to be greater than 1. And the reason for that is because for the same reason, when we square u and then subtract 1, we need to make sure that that's going to be a positive value. Otherwise, we end up running, we would have the square root of a negative number, and again, it would be imaginary, and then the derivative would not exist. So these are the derivatives of your inverse trig functions. The best way to deal with these is to commit them to memory, and hopefully this helps. Good luck, and I'll see you in the next video.